Hello students, I am Dr. Sanjeev Ponia. In last lecture of computer architecture, we discussed about the number system. First, we discuss about the central processing unit. Then we discuss about the control unit that there are two parts. First one is control unit and second one is arithmetic logic unit, and we discuss that what's the need of number system to study arithmetic logic unit. Then we discuss different type of number systems based on decimal value, based on natural values, whole numbers, real numbers. We discuss different type of number systems, and in the last we discuss about weighted and non-weighted number system. In today's class, we will discuss about binary number system. As we know that every work has to be performed in binary numbers in computer. So we will discuss binary number system and its representation, that how it is going to represent when we have to represent it in different form, or the different forms in which we can represent a binary number system. So as I told you in last slide that there are different numbers based on radix, and these are binary, octal, decimal, and hexadecimal. We discuss that the representation or the value of a number depends on the base of that particular number, and the weight or that is value of that particular digit depends on the number of place that where it exists. And second thing, I taught you that base tells that how many different digits we have in that particular number. For an example, in binary number system, there are two different digits, that is 0 and 1. Base is 2. It represents that there are two different digits, 0 and 1, and we can represent a number that is 11110000 base 2. It is going to represent that we are dealing with a binary number. Then in the octal, the base is 8. It represents that total number of different digits in octal number are 8, that is 0 to 7. 1, 2, 3, 4, 5, 6, 7, 8. So there are total different digits. We can make any number by using these different digits. For an example, this is a octal number, that is 360, and this 8 represents the number system that we are dealing with, octal number system. Then the decimal number system, that we are using in our day-to-day life. Here, the base of decimal number system is 10. It means it has total 10 different digits from 0 to 9, and we can represent any decimal number by using any of these digits. So, for an example, this is the representation of a decimal number. It contains 2, 4, 0, and 10 represents the base of the number, that it's a decimal number. Next is hexadecimal. Hexadecimal number system contains base 16. It means there are 16 different digits in a hexadecimal number that starts from 0 to 9. These are total 10, and 10 is going to represent by A, B 11, C 12, D 13, E 14, and F 15. Means total are 16 digits in a hexadecimal number. And we can represent a hexadecimal number by using any of the bit among these. So for an example, F0 represents a hexadecimal number, and this 16 represent that the base of this is 16. It means it is a hexadecimal number. So this was the concept behind between different number systems that we are using in digital electronics, as well as we have to study for the use of computer application. But especially we are going to concern with binary number system to discuss computer arithmetic. So now we will discuss binary number systems, and in one example we will try to understand that how we can convert a binary number system to decimal number system, or a decimal number system to a binary number system, because it can be given in the example that we have to perform an arithmetic operation for 21 plus 13. It may be given that we have to find out or to write an application, a program where two numbers, that is 21 and 13, has to be added. So for that we should know that how to convert these decimal numbers into binary numbers. So the way to convert a decimal number system in binary number system is as follow. This is 17 in decimal. This is a number 17 in decimal, and we have to find out binary equivalent of 17. So first we write 17 as it is, the number that is given, and divide it by 2. Divide it by 2. We have to write the quotient. So this is 2 8 just 16. So quotient is 8, and remainder is 1. So write the remainder in front of it. Write the remainder in front of it and quotient below. Then again we will divide 8 by 2. So this is 4 and remainder is 0. Again we are going to divide 4 by 2. So the quotient is 2 and remainder is 0. Again when we are dividing this 2 by 2, then remainder is 0 and quotient is 1. So this is the way to represent a binary number, that is we have to start from left to right in the bottom and then from bottom to top, and this is the binary equivalent. So here first we will write this. So this is first we write 1, then it's 0, then 0, then again it is 0, again it is 0, once more it is 0, it is again 0, and in the last it is 1, it is 1. So this is the binary equivalent of this decimal number. We learned this earlier in the digital electronics as well as in the revision section of computer architecture. In the same way, we can find out the binary equivalent of a octal number system as well as hexadecimal number system. But we are not concerned with this over here. This is not our motto. Our motto is to study the computer arithmetic, and to study the computer arithmetic, we have to study the binary number system. So this is the reason I gave you an example that how we can convert a decimal number system to binary number system. So I hope this concept is clear to you as we revise this. Now, when we have to study a binary number, then it starts from 0, 1, 2, 3 till n minus 2 and n minus 1. For an example, I am saying that I have a number 7, and when I am converting this number 7 into binary, then this is the binary equivalent of 7. This is the binary equivalent of 7 when I am using 4-bit number to represent 7. So this bit that is in the right is represented by position 0. This bit is going to represent by position 1, and the last bit, that is this 0, is going to represented by n minus 1, and n is 4 over here. This is 4 minus 1, that is 3. Means the last bit is going to represent by n minus 1, that is 3 in this case. So in the general form, we can say that if we have a n bit number, then that number can be represented by the position 0, 1, 2 till n minus 1. So this was about the bit position of a number. Then this is the digit of the number. This is the digit of the number, as in this binary case, this is the zeroth digit, this is the first digit, this is the second digit, means it is 1, 1, 1 and 0. And when I told you that in case of positional number system or weighted number system, we have to find out the values of each digit, because value of same digit as different place can be different. So when we are going to calculate the value of this digit, that is A0 at position 0, at position 0, as we are studying binary number, so this is 2 raised to the power 0, this is 2 raised to the power 1 for first position, for last position this is 2 raised to the power n minus 1, as the weight depends on the position, as the weight depends on the position, and this is a binary number, so we are going to find the weight of different digits. So weight corresponding to this digit, weight corresponding to this digit is 2 raised to the power 0, as the position is 0. The weight corresponding to this digit is 2 raised to the power 1, and the weight corresponding to n minus 1 position is 2 raised to the power n minus 1. This bit, that is A0. A0 is called LSB, least significant bit, whereas AN minus 1 is called MSB, that is most significant bit. For an example, I have a number 10 010 then in that case this zero represents LSB, means least significant bit, whereas this one represent MSB, that is most significant bit. Here we discuss about the position of a number, about different digits of a binary number, and the weights corresponding to different position in a binary numbers. So this concept should be clear to you now, as we studied this thing earlier also. So this is the representation of a binary number when we have to find out the weights of corresponding digit. The position is going to start from 0 to n minus 1. When we have a n bit number, the digits are going to represent by A0, A1 to an minus 1, and the corresponding weight is going to be find out by 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power n. And this bit, the rightmost bit, is called least significant bit, whereas leftmost bit, that is a n minus 1, is called most significant bit. So this was the overview of a binary number system. Here we discuss the conversion of a number into binary number system. Now we will see that how we can represent different binary number systems in different form. So when we are dividing the binary number system, then it can be represented in unsigned representation and signed representation. As I told you that there are two types of number, positional number and non-positional number. Here we are dividing these binary numbers in unsigned numbers and signed numbers. When there is no sign, means no sign is given, then we will consider those numbers positive. For an example, 5 is a positive number, 832 is a positive number. So this is unsigned representation of a positive number. On the other hand, we can represent it using signed representation. Using signed representation, maybe this is minus 5, minus 8, like this. So here in signed representation, we have to represent a number using sign. This is for the negative number. If I want to represent a positive number over here, then I can write plus 5. It represents that my number is a positive number. My number is a positive number that is in the form of signed representation. Means in signed representation, we can represent a positive number as well as a negative number. When we are discussing to represent a negative number, then the negative number can be represented in three forms. Negative numbers can be represented in three forms. First one is sign magnitude form. Second, ones complement forms. And third is two's complement form. When we have to represent a binary negative number, then there are three ways to represent a binary negative number. First one is sign magnitude form, second is one complement form, and third is two's complement form. Leave these ambiguities, or this one ambiguities, or this one unambiguity at this moment. I will discuss this after time being, within a moment. So the purpose over here is to tell you that how we can represent a binary negative number. So this was the basic concept. Now we will see that how we can represent these numbers. First one, that is unsigned form. Over here, first one is signed magnitude form, and before this we divide these binary numbers in unsigned and signed. Unsigned and signed representation, and unsigned means positive numbers. So if I have a number A where the number is of 1 bit, no, this A is of 1 bit, then the value of A can be either 0 or 1. Either 0 or 1. When I have 1 bit number, then the values can be 0 and 1. When I have a 2-bit number, suppose I have A and B, then different possible combinations I can make for these, that is 0 0 value of A and B both can be 0. Value of A is 0, B is 1, value of A is 1 and B is 0, and value of A and B both are 1. So this is the total possible combination. We can find total possible combination by 2 raised to the power n when we have n bit number. We can prove this from here that when n is equals to 1, so 2 raised to the power 1 equals to 2. So it means total value is, sorry, 2 raised to the power 2 raised to the power 2. Yes, this is 0 and 1. When this is 2 raised to the power 2, in case of 2 bit, so this is 2 raised to the power 2, that is 4. So total possible combinations are 4. In case of 3, 2 raised to the power 3 is 8, and in case of 4, 2 raised to the power 4 is 16. So these are possible different numbers we can write by using different bits of number. As we see, when we have 3 bits, then I can write a number from 000 to 7. 000 to 7. When I have a 1 bit number, then I can write a value from 0 to 1. From 0 to 1. When I have a 2-bit number, then I can write a value from 0 to 3. So this is the way to find that how much the value of a number can be when I know the number of bits in binary number. Maximum number of representation can be found by using 2 raised to the power n, where n is the number of total bits. Now, this is sign magnitude form. Okay, we complete this. Yes, we will complete this. So this was about the unsigned numbers. This was about the unsigned numbers. Now we will try to understand in case of signed number. Means when we have a number of minus. Suppose I have a number that is plus, or I have a number plus 5. Then I can represent this number in 4 digits, or this number is equivalent to 0, 1, 0, 1 in binary when I have a 4-bit number to represent plus 5. This is the reason I told you that we should know the conversion of a decimal number system to binary number system. So 5 can be represented by 0, 1, 0, 1. This we can represent in unsigned form. But when we have to represent this in signed form, means we have to represent minus 5 also. Then in signed form, what we do, we keep the first bit, that is most significant bit, to save the sign of the number, that the number is positive or the number is negative. That is explained by this most significant bit. So whatever the length of a word I have, for an example 4-bit number or 8-bit number, we are not going to bother at this time. Our purpose is to understand the MSB only. As I told you, that first bit from the left or leftmost bit is called most significant bit. So in signed form, we use the most significant bit to save the number that it is a positive or it is a negative number, where 1 is going to represent a negative number, and if there is 0 in MSB, then it is going to represent a positive number. Means this is a sign bit. So this is equivalent to 4 in the decimal as 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2. So first 2, that is 2 raised to the power 0, this is also 0, this is also 0, as these are going to multiplied by 0, and place value of 2 raised to the power 2 is 4. So when this 4 is going to multiply with 1, so we are getting a 4. And because of this one, because of 1 in MSB, it representing that this is a minus 4. And when it is a positive number, then it is going to represent by 0. The range of these numbers are minus 2 raised to the power n minus 1 to 2 raised to the power n minus 1 and minus 1. For an example, I have a 3-bit number. As I told you in the last slide, that we can store 7 bits over here. We can store up till 0 to 7 decimal numbers over here. So this is 2 raised to the power n minus 1, that is 2 raised to the power 3 minus 1. As this is a 4-bit number and first bit we are using for the sign, so we are considering only 3 bits to save the number, because the first bit save the sign and rest of the bits save the magnitude of the number. So when we have a 4-bit number, it means we can store only 3 bits. And when we can store a 3-bit number, then it is 2 raised to the power n minus 1. So 2 raised to the power 4 minus 1, that is 2 raised to the power 3 minus 1. And 2 raised to the power 3, it is equals to 8. So 8 minus 1, that is 7. So this is 7. So range is, this is 7. So range is from minus 7. Range is from minus 7 to, this is 2 raised to the power n minus 1. We calculate it just now. So this is minus 7 to plus 7. So range in these numbers are minus 7 to plus 7. One more example to clear this concept is, if we want to represent a 5 number in decimal in signed magnitude, then it will be, as this is a 4-bit number, so first bit represents the sign that this is a positive number, and 101 is equivalent to 5. And when we have to represent minus 5, the first bit, that is MSB, represent a negative number, and this is equals to 5, so it represents minus 5. The problem in this number is that if we have to represent a 0, if we have to represent 0, and the 0 can be plus 0 or minus 0. So in case of plus 0, the first MSB will be 0 and rest of the numbers will also be 0. In case of minus 0, the first one represent that this is a minus number and this represents 0. So problem is that there are two representations of 0. Plus 0 has different representation and minus 0 has different representation. But we have only one number, so it should have one representation. As I was telling you earlier that we will discuss about the ambiguity later on. So this is sign magnitude form, and you can see from here that I wrote it that this is ambiguous, as there are two representations of 0. Sign magnitude form is ambiguous as there are two representations of 0, and this is also in the case of one representation we will see now. So let's see what happens in one's complement. In one complement, we have to total all the bits. Suppose I have to write -5, then first of all I will write the binary representation of 5, that will be 0 1 0 1. There in first complement we never use 0 or 1 for the positive or negative number, that is in sign magnitude form. Over here we have to write only the value of positive number, as I wrote the value of 5, and when we have to write a negative number of this number, then flip all the ones to zeros and zeros to 1, as it will convert, this one will convert in 0, this 0 will convert into 1, this one will convert into 0, and this 0 will be totaled by 1. So this is the binary equivalent of -5. So when we have to find out the binary equivalent of a negative number, then we can write the positive number and write the negative number of that is one complement of positive number by total all bits from 0 to 1 and 1 to 0. For an example, I want to write -8, then in that case first I will write the value of 8, and 8 is equals to 1 0 0 0. When we have to write -8, then it will total from 0 to 1 0 to 1 0 to 1 and 1 to 0. So this is the binary equivalent of -8. This is the binary equivalent of -8. Here is also the problem of ambiguity, as I told you that 0, there are two representation of 0. When I am writing the value of 0, this is 0 0 0 0, and as I told you that when we have to find out the ones complement of a number, then we have to total all the bits from 0 to 1 and 1 to 0. So when I am totaling these bits, then I am getting 1 1 1 1, and it represents that there are two representations of 0. Sorry. So now we will study about the 2's complement, and the ambiguity problem is going to solve in 2's complement. In this, when we have to find the 2's complement of a number, when we have to find the 2's complement of a number, then first we have to write the 1's complement, and after that we have to add 1 in 1's complement. For an example, I have to write -5 in 2's complement. Then to find -5 in 1's complement, I have to write +5. So this is the representation of +5. When I have to represent this in one complement, then I have to total 0 to 1. So it will convert from 0 to 1, sorry, 1 to 0. This will be from 0 to 1. This will be from 1 to 0, and it will be from 0 to 1. So this is the one complement representation of a 5, and when I have to find out the two's complement, then we have to add 1 in one complement. So this is one complement, I add 1 in this. So this is 1 plus 0 is 1, this is 1, and this is 0, and this is 1. So this is the 2's complement of minus 5. This is the 2's complement of plus 5 to represent minus 5. Here the problem of ambiguity to represent 0 is also has been resolved, means there is only one representation of a 0. When I am writing the value of 0, that is plus 0, is it equals to 0, 0, 0 and 0. When I have to write the 2's complement of this, then first I have to complement, I have to total all the numbers from 0 to 1. So this is 1, this also 1, this also from 0 to 1, and it is also 1 from 0. This is the one complement. To find 2's complement, I have to add 1 in this. So after adding 1 in this, this is 0, 0, 0, 0, means all 0. So in this case, the representation of plus 0 and minus 0 is same. So there is no ambiguity in this case, and the range of this is minus 2 raised to the power n minus 1 to plus 2 raised to the power n minus 1 and minus 1. There is one direct method also to find the 2's complement. Suppose I want to find out the 2's complement of 9. 2's complement of 9. Then this is equivalent to, means I can represent this number in binary form 1001. 1001. This is the binary representation of plus 9. When I have to find out the 2's complement of this number, then start from right to left, and when first one comes, write that one as it is. When we are starting from here to here, then first digit is the 1. So write this digit as it is, and after that total all the numbers, that from 0 to 1 and 1 to 0. So this will be, and instead of 1 it will be 0. So this is the 2's complement of plus 9. Same way, suppose I have a number 1 0 1 0 0 1 0 0, and I have to find out the 2's complement of it directly. Then I will start from right to left, and I will check that is this digit is 0 or 1. When I will find first digit 1, then I will write as it is and rest of the bits I will total. The the first bit from the right is not 1, so write it as it is. The second bit is also not 1, so write it as it is. The third bit is 1. So we have to write this bit as it is, and after this we have to total all the bits from 0 to 1 and 1 to 0. So this 0 will convert to 1, this 0 will convert to 1, this 1 will convert to 0, this 0 will convert to 1, and this 1 will convert to 0. So this is a direct method to find the 2's complement of a number. By this way, we can find the 2's complement of any number by using direct method or indirect method. This was the representation of integer. You can compare from here also that in sign magnitude form, one complement form and two complement form. I try to represent these over here. So from here you can see that in sign magnitude form, first bit represents sign. So this is a positive number. This is a negative number. So there are two representations of 0, that is 000 and 100. In one complement also there is two representation of 0, that is 000 and 111. Only there is 2's complement where the representation of 0 is only 1, that is 000. So this is the reason that everywhere in computer, instead of sign magnitude or ones complement, we are going to use the two's complement form to add, subtract, multiply, or to perform any calculations with negative numbers. So this is about the integers number. Now when we have to study about the floating point number, then we will discuss about the representation of floating point numbers also, as this is the brief that first bit is used to show the sign, as this is in sign magnitude, and these bits are used for the exponent, whereas these next bits are used for the significand. So we will discuss this when we will study the floating point numbers. So in the next lecture, we will discuss about the arithmetic operation. In today's lecture, we discuss that how we can represent a binary numbers, what are the different binary numbers, how we can convert a decimal number system in binary number system, what is MSB and what is LSB, then representation of binary number system in unsigned form and signed form. Then in signed form, we discuss that how we can represent a negative number in sign magnitude form and one complement form, as well as 2's complement form. We discuss the problem of sign magnitude and 1's complement form, as there are two representations of 0, whereas in 2's complement there is only and only one representation of 0. So all the problems have been solved using 2's complement. Then we discuss to find out the 1's complement and 2's complement. So this is all about the today's lecture. In next lecture, we will discuss about the arithmetic operations, that is addition, subtraction, etc. Thank you.